first lesson today gets into a concept called limits. And limits are really more of a pre-calculus topic. They are a concept that we need to understand to sort of understand why the rest of calculus works the way it does. Okay, so what we're doing today actually should seem pretty simple as far as limits go. Here's sort of the easiest definition of what a limit is. It's the value that a function approaches as x approaches a given value. That sounds like a lot of the same words all kind of mashed together, but I do want to point out that the value of a function is talking about the y value. So what we're really doing is we're looking at what is the y value doing as we get closer and closer to a particular x value. Okay, so we're moving towards a certain x value, meaning we're moving left or right on a graph, and we want to know what is the y value doing as we get closer and closer to that spot we're trying to get to. This is the notation you're going to see us use a lot. This is saying the limit of this function, f of x, as x approaches c, which c will represent some number, is, and I used a y value here, but this will be a number of some kind, okay? So we're going to start with an example that is really boring, okay? That there is not a lot of exciting things happening in this first example, and you'll see why, but we have to do a boring one for you to understand a non-boring one, okay? So this right here is the function that's described here, x cubed minus 2x. And I want to know what's the limit of this function, meaning what are the y values doing, as x is getting closer and closer to negative 1. So let's just kind of mark for ourselves where negative 1 is. Here's negative 1, right? So I'm going to kind of build a wall at negative 1. And then I'm going to walk along the highway that is my function. Okay, so I'm going to walk in from, this would be maybe east to west. Doesn't really matter. I'm making things up here, but I'm moving in this direction toward that x equals negative 1. Or I can move in from this side, so I can move kind of west to east. I can move to the right, and I'm climbing this way. But either way, both directions are approaching this particular value. Okay, so if I were to look at these y values, we start out at, whatever this y value is, and it's climbing and it's climbing and it's climbing, and the y values are going to increase and they're going to keep increasing until I get to this point at negative 1. Over on this side, as I approach here from the right, these values are going to increase and increase and increase, and they actually go over that value, right? Up here, we're actually above where that point is. But then they start to creep back downward until I hit this negative 1. And so coming in from both directions, as I approach x equals negative 1, my y values are getting closer and closer to 1. So I'm going to say that this limit here is equal to 1. Now let's do the same thing at x equals 0. So here's where x is equal to 0, right? Here's my wall at x equals 0. And I'm going to walk along the highway of my function. So I'm going to walk in from the left side like this. And I'm going to walk in from the right side like this. Okay. And on both sides, again, I'm approaching this y value right here. Okay. So as I'm approaching from the left side, my y values are shrinking. They're getting closer and closer to this y value here. As I'm coming in from the right side, my y values are actually negative, but they're increasing, right? They're getting bigger and bigger and bigger until they hit this y value right here. And so on both sides, I'm approaching this y value, which is right on the y-axis, meaning that value is 0. Okay, here's why this is the most boring problem ever. We didn't really need to do a limit here, right? This function at negative 1 is just equal to 1. Okay, so of course the limit as we're approaching negative 1 is going to be 1 because, and I'm going to just make this note for later because this is going to be important later, is if I find the function value at negative 1, it would just be 1. Same thing here. This function is just equal to 0 at 0. So the limit thing feels a little pointless right now. Okay, and I get that. You're going to learn why this is a boring one later in this chapter, but it has to do with the fact that this is a boring graph. There's nothing big happening here. It's a nice, continuous, just regular old polynomial function. There's no exciting asymptotes or anything like that. And so these ones, as far as finding limits, feel a little bit like, okay, what was the point? So let's take a look at the next one. Oh, you know what? I'm sorry. I missed that there's this example here. This example is a little bit different in that it has us going to infinity. It says x approaches infinity. That is actually a concept that's going to come up much later in the chapter. We don't really need to talk about it now, but just so you can get the idea of what this is looking for, is instead of approaching a particular x value, I just want to know as my x's get bigger and bigger and bigger, meaning here's the direction that my x's are getting bigger. If I walk forever to the right, but I have to stay on the highway of my function. So this is me walking forever and ever and ever to the right. My y values are doing this, right? They're climbing and climbing and climbing as I'm moving to the right. And this is going to go up forever and ever and ever and ever, as far as I know. I mean, I don't see anything where this graph is going to turn around and come back the other way, okay? And so if this is going up forever, we call this positive infinity because this graph is climbing forever and ever and ever. So for now, I'm just going to say that this limit is actually infinity because as x goes to the right, my y values go up forever and ever and ever. Okay, we're going to revisit this concept much later in the chapter, and actually later in this lesson, I'm going to come back and say one more thing about it too. Okay, now let's look at a graph that's maybe a little more interesting. I use that word loosely. This is a piecewise function. So you'll see that this graph looks like a nice normal graph, right? Except it's got a hole in it. So this function, it's a piecewise function where the entire function is defined by this thing, except at x equals 0. This is saying at x equals 0, my value is -1. So that's why you'll see this hole here. And then down here, you'll notice there's just a lonely dot down here at -1. Okay? And so the interesting place to actually talk about a limit is at that value x equals 0, because that's where there's a break in the graph, right? So if I do the same thing, if I say that I'm approaching 0, so here's where x is equal to 0, I'm going to approach from the left, I'm going to approach from the right. And if I look at those y values, they're climbing and climbing and climbing and climbing, getting closer and closer to this y value here. Same thing here. These y values are climbing and climbing and climbing and climbing, getting closer and closer to this y value here. So on both sides, I'm approaching this same spot, and the y coordinate there is just +1. Now, so that is the limit. That's a little bit weird, though, because there's a hole there, right? So in this case, the limit as we approach 0 is 1, but the actual function value, so if I were to plug 0 into the function, it's not 1, it's -1. So these two things don't match. That's going to be important to us mathematically. It's not important to us today because it's going to get into the definition of continuity, which is going to come up later in this chapter. But I just want to kind of draw your attention to that like that's why these piecewise functions are important for us to talk about, because this is where we start talking about what makes a graph be continuous. Okay, onward and upward. Okay, so here's another piecewise graph, and this is a piecewise graph that's not even connected, okay? And of course, that place where it's broken, that place where there's a gap, that's where it's going to ask us to find the limit. It's going to ask us to find the limit as x approaches 1. And just pay attention to how this graph is numbered here. So 1 would be this value right here, okay? And so this is where x is equal to 1, is along this line here. And I'm going to have that same conversation with myself. I'm going to walk in along the highway from the left. I'm going to walk in from the right, and we're going to see where we get to. So coming in from the left, my y values are going here. Coming in from the right, my y values are going here. Okay? These limits land in two completely different places. This one lands here, this one lands here. Okay? So I'm actually going to pause on answering this question right now because I want to talk about the stuff that's down here and what it really means to be a limit algebraically, and then we'll come back and actually answer this question. So let's jump down to where it talks about one-sided limits. And I don't really remember how much of this I have pre-printed for you versus you have to copy in. So if at any point you need to pause the video to copy some things down, you certainly may. Okay, so when we're talking about that whole idea of walking in from the left and walking in from the right, that's what this notation is talking about. And I actually might try to zoom this in some so you can see that. If I'm coming in from the left, I use a little negative sign as a superscript here. If I'm coming in from the right, I use a positive sign, which should make sense to you because on a graph, the left side of the graph is negative and the right side of the graph is positive. Okay, so this is a limit approaching from the left. And this is a limit approaching from the right. And that kind of notation is going to be important for this algebraic definition of a limit, which, by the way, this is super important. Okay, so if this is not written in your notes, you're going to want to write this down. So given a function f of x and an x value x equals c, so this is just kind of the setup for how we write limits, right? We talk about a function, we talk about a specific x value that we're approaching. This says that the limit as x approaches c is this number L, so again, L just represents a number, if and only if the limit coming in from the left is equal to the limit coming in from the right. Sometimes you'll see me kind of abbreviate this as like the left-handed limit is equal to the right-handed limit. Okay, this is a much more technical way to write it, but LHL, RHL, that's left-handed limit and right-handed limit. The only way we can say that a limit exists is if this is true. If the coming in from the left and coming in from the right lands us in the same spot. Now, it's okay if we have one like that last example we did, where we have a hole in the graph when we actually get there, as long as both sides are heading to the same place. Okay? So that's when a limit exists. Okay, this is when a limit exists. So let's talk about when a limit does not exist. And this is going to happen from time to time too. We use this abbreviation DNE, by the way, that represents does not exist. Okay, and we can say that a limit does not exist if this breaks down. So if the left-handed and the right-handed limits do not end up in the same place, the limit does not exist. You're not going to get to these yet because right now we're just talking about graphs. But when we start doing this algebraically, if you end up with a limit where it's a number over 0, we know that's not allowed, right? So that's a limit that doesn't exist. And then this one's interesting and also kind of controversial in math land. A graph that goes to infinity or negative infinity, sometimes you'll see some textbooks and some mathematicians that say that limit does not exist. And that's because if a graph goes up and up and up forever, there's not really a limit on it. So I'm going to take this as an opportunity to switch back to that first page real quick and talk about a couple of things. And again, if you need to pause or backtrack the videos to be able to write those things down, please do. So with this first one, again, coming in from the left, coming in from the right, we were going to land in the same spot because that's just what the value of the function is, that place. This one here, the limit exists because coming in from the left and coming in from the right, we're still going to the same place, even if it's not the actual function value, okay? But that third one we looked at where the lines were going to two completely different places, that's when we would say the limit doesn't exist. This one here, where we said the limit was infinity, this is kind of what I'm talking about, is that if this graph goes up and up and up forever, we might say that that limit does not exist because there's no bound. There's nothing like actually limiting our graph. There's nothing stopping it from going anywhere. Okay, so heading back to this example, let's answer this question for real now. What is the limit as x approaches 1? Well, the left-handed limit and the right-handed limit are going two completely different places. And so to answer this question, I would say this limit does not exist. Okay? And if I had to justify this, and this is going to be important that you're writing this with proper notation and all of that, I would say something like the limit of g of x as x approaches 1 from the left. As we're approaching from the left, that value is equal to 1. And that is not equal to the limit as we approach from the right. So x approaches 1 from the right side, where this limit would land us at -2. Okay, oh, and I gotta have my g of x in there. But this is the way you're going to justify anytime you're saying that a limit does not exist. You're going to say the left limit and the right limit do not equal each other. Okay, actually, it wouldn't even matter if I put the values, like if I put the 1 and the -2 in there, as long as I state that the two limits are not equal to each other. Okay, I'm going to pause that there. I'm probably going to do a new video with the next few examples in it, just to kind of break up the monotony here. And yeah, we'll pick up in a few minutes.